Hi, it's time for another math easy solution to discuss further into modeling with differential equations and look at example 2 of the example series, and this time look at basically this example will deal with the initial value problem, and I'll go over that in a bit. Yeah, basically when applying differential equations, we are usually not interested in finding a family of solutions called otherwise called the general solution, and these are the ones that I went over in my last video and other videos as well, especially example 1, which I went over a general solution. And the reason is because we are more interested in finding a solution that satisfies some additional requirement instead. Basically, in many physical problems, we need to find the particular solution that satisfies a condition of the form y of t0 is equal to y0 or y naught. I think that's how you call it in some areas. Yeah, it was when I was doing engineering in school, they called it y naught. I don't know why. So basically, yeah, this is called an initial condition. So basically, instead of finding pretty much every solution, all we want is a solution that matches whatever initial condition we have. And the problem of finding a solution of the differential equation that satisfies this initial condition is called an initial value problem. So that's pretty much what initial value problem is. Geometrically, when we impose an initial condition, we look at the family of curves and basically just pick the one that passes through here if you were to graph it. Yeah, and basically, physically, this corresponds to measuring the state of a system at time t0 and using the solution of the initial value problem to predict the future behavior of that system. Basically, if you were to look at a graph of a bunch of solutions to, let's say, any given differential equation, let's say it's something like this, etc. I'm just drawing the general family of curves like this, but then our specific case is, let's say we had let's deal with t instead of x. It doesn't matter which one you use. And let's say at this very point, this is at the point t0 and y0. And in this case, t0 is equal to 0. And basically, this is the solution. So this is the solution that we are looking for, and we'll call this y1 or something like that, or yi or whatever. So let's call this yi. These ones could be all y2, y3, different solutions to that differential equation, but the only one we're interested in is this one. And then if you look at it again physically, if this is the one we impose on it, everything else in the future, if you're looking at time, is a prediction based on your initial value problem and that differential equation. So now let's go over a quick example just to illustrate how to go about solving a particular solution. So this example states, find a solution of the differential equation from the previous example, and I'll write that down, that satisfies the condition y0 is equal to 2. And basically recall from my earlier video, my last video, that the differential equation was y prime is equal to 1/2 y squared plus 1. And also recall that I showed that the solution, the general family of solutions, so I'll write general solution, was also shown to be in my last video, so make sure to watch that. It's in the video link below. It was shown to be y is equal to 1 plus c times e to the t, and then 1 minus c e to the t, where the c is a constant. So basically, in our case, we need to find the value of c. So then again, this c, I was right actually, where c is constant. This is just a constant value. So that's a constant, and we got to find that specific value of it. So what we'll do is use our initial value that we're given. So y of 0 is equal to, it's equal to 2. So what we could do is plug this into our general solution right here. So what we'll end up having is 1 plus c e to the 0, 1 minus c e to the 0, and then again e to the 0, anything to the power of 0 is equal to 1. So what we end up having is this just becomes 1 plus c, 1 minus c like this. And again, this equals to 2. That's there. So what I'm going to do is multiply this onto this side. And just move this over by multiplying both sides by 1 minus c. So what we end up having is 1 plus c is equal to 2 times 1 minus c. Multiply this out. This is just 2 minus 2c. And now what I'll do is move the c onto over this side, all the c's, and then all the non-c's over to this side. So to do that, we add 2c on this side, and then add 2c on this side. So we get 3c is equal to, and this we subtract 1, we get 1. So rearrange this, c is equal to 1 over 3. So this means that our particular solution, so then the solution to the initial value problem, or I'll write particular solution that we wanted, is basically y is equal to 1 plus 1/2 e to the t divided by 1 minus 1/2 e to the t. So this is our solution, but let's just simplify this a bit further by multiplying both sides by 3. I'm going to do 3 over 3, so that when you multiply it in, this 1/3 cancels. So what we end up having is y is equal to 3 plus, and then that just cancels, it becomes 1 e to the t, just to make it neater. 3 minus e to the t, and this is our particular solution for the initial value problem. And again, yeah, so this is just one solution, and then as opposed to the general solution here, which is just a bunch of curves, although ours is just one curve. And again, here's the idea. Yeah, there's a bunch of curves, we only pick the one we want. Anyways, that's all for today. Hopefully you'll learn from this this brief video on initial value problems, and hopefully you'll learn. And like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.